Okay, so let's go through this problem together. This is one of our beginning wave problems, and I just want to make sure that we're all clear on a lot of the vocabulary. And this is going to overlap with some of the information for simple harmonic motion when we studied springs before. So hopefully this will serve as part of review for springs. All right, so what we have here is a graph. It's the motion of a wave. This is its vertical displacement versus time. We don't have any information right now about its horizontal displacement, but just by looking at this graph, we can tell that the amplitude of the wave, and that's the distance between the resting point to its maximum or its minimum position, is 15 centimeters or 0.15 meters. They've asked us about the wavelength of the wave, and so normally what we do is we take the position from crest to crest or trough to trough, and we can read from the graph the displacement of the wave. But in this particular case, we don't have any displacement in the horizontal position, so we're not really sure about this. I think we're going to have to say that it's not possible from this particular graph to be able to figure it out. Remember, we could rearrange the formula for velocity equals frequency times lambda, and we could get lambda by algebraically rearranging, but we would need to know the velocity of the wave. And if you go back up here, it doesn't look like they've given us that information in the problem, but we'll come back to this. All right, so what's the period of the wave? Well, remember that's one repeating cycle for the wave. And so the crest is 5 seconds up here and 25 seconds. So we have a period of 20 seconds. And the relationship between period and frequency is an inverse one. So 1 over the period will give us the frequency. That's 1 over 20 seconds. So that's 0.05 hertz. They'd like us to tell them the horizontal velocity of the wave. Well, it looks to me like we have the same problem that we had above. Then in order to find the velocity, we need the wavelength, and we weren't provided the wavelength, so that's not possible either. All right. And our last question is, what's the vertical speed of a single point on the string? So now that's an interesting question because you get a lot of information off this graph, but if you remember from our springs, the point right here, when this string reaches this point, the velocity is actually equal to 0. And when the string gets all the way to the equilibrium point, well, that's the maximum velocity. And again, when we get all the way over here, the velocity is equal to 0. So you could find the average velocity. Well, the average velocity would be the displacement for a wave. And so our change in displacement, it goes from 15 centimeters all the way down to 15 centimeters and back again for one full cycle. So the displacement for one cycle would be 60 centimeters. And that takes the wave 20 seconds to pass through that point. And so you'd have an average velocity of 3 centimeters per second. But imagine that we'd like to know the velocity at a particular point. Well, then we'd have to use our Vmax formula. And this comes from rearranging the simple harmonic equations. But we get an equation that is equal to, let's see if I can find that equation. So it is the 2 times pi times the frequency times the amplitude of the wave. And so what do we get? We get 0.15 centimeters times 2 times pi times 0.5 hertz. And we get a maximum velocity. Let's see. Good Lord. 4.7, sorry, 4.7 centimeters per second. All right. Okay. I think that's all we can do on this one. Yep, that's it. All right.